Picture yourself standing on a platform. You feel the rails begin to vibrate beneath your feet. The air shifts, and then 180 tons of steel blurs past you at 200 kilometers per hour. It is not magic, it is physics, engineering, and over 200 years of machines that quietly reshaped civilization. Today, we are going to answer one deceptively simple question. Why are trains so extraordinarily powerful? Where does that force actually come from? And how did it all begin? Let's go back to 1804. Wales, Great Britain. An engineer named Richard Trevithick builds something the world has never seen. The first steam-powered locomotive capable of running on iron rails. The machine hauls 10 tons of iron ore and 70 passengers across nearly 15 kilometers of track. Its top speed, 8 kilometers per hour. Nobody laughs, because nobody has ever seen a machine move itself and drag that kind of weight behind it. 21 years later, in 1825, George Stephenson opens the first public railway in the world, the Stockton and Darlington Line. His locomotive, called Locomotion No. 1, produces around 15 horsepower. Think about that for a moment. 1 horse was the benchmark for raw pulling strength. 15 of them concentrated into a single iron machine. That was a gap you could feel in your chest. So how did steam actually work? In simple terms, water heated inside a boiler turned into pressurized steam. That steam drove pistons, which turned wheels. The higher the pressure, the better the boiler, the greater the power output. It is a straightforward principle of thermodynamics. Thermal energy converted into mechanical motion. And that principle ignited a race that lasted the entire 19th century. Engineers competed to build bigger boilers, more efficient valve systems, better cylinders. In 1938, the British steam locomotive Mallard hit 236 kilometers per hour, a world speed record for steam traction that has never been broken. Its peak power output exceeded 3,000 horsepower. 3,000. To put that in perspective, that is roughly equivalent to stacking 18 Ferrari 488 sports cars into a single drive train. In 1938, steam had its limits though. It demanded water, coal, and constant skilled attention. By the mid-20th century, 2 new technologies stepped in: diesel engines and electric traction. Diesel locomotives became the dominant choice wherever electrifying a line was too expensive or impractical. A modern diesel locomotive like the Siemens Vectron, a type widely used across Europe today, delivers up to 3,300 kilowatts of continuous power. Let's translate that. 1 kilowatt equals roughly 1 1/3 horsepower. 3,300 kilowatts works out to nearly 4,500 horsepower. Compare that to something most people know, a standard family car. A Volkswagen Golf produces around 150 horsepower. To match a single modern diesel locomotive, you would need to take 30 of those cars, rip out every engine, and somehow merge them into one. 30 Golfs. That is 1 locomotive. 1. But the real revolution came from electricity. Electric locomotives draw power directly from the grid. Through a pantograph sliding along an overhead wire, or through a third rail. They carry no fuel. They waste no energy running an onboard generator. The result is an efficiency that diesel simply cannot match. The clearest example: the Siemens ES64U4, known in Poland as the Taurus, operated by PKP Intercity and several other European carriers. Its continuous power output is 6,400 kilowatts. That is over 8,500 horsepower. The locomotive weighs 90 tons and can pull a train weighing up to 1,200 tons. 1,200 tons of passengers or freight pulled by a single machine drawing electricity from a wire above its head. Numbers on their own are easy to ignore. So let's make them real. A typical European freight train hauled by an electric locomotive moves between 1,000 and 2,000 tons of cargo in a single run. A heavy articulated lorry, the biggest trucks on our roads, carries a maximum of around 24 tons per journey. To move what one freight train moves, you would need between 40 and 80 trucks on the road simultaneously. 80 lorries. One train replaces them all, and does it using several times less fuel per ton of cargo per kilometer. That is not just power, that is efficiency at a scale that changes the economics of an entire industry. A Boeing 737-800 has a maximum takeoff weight of 80,000 kilograms, 80 tons. Its engines produce a combined thrust of around 200 kilonewtons. Impressive, no question. But the Japanese Shinkansen N700, one of the world's most famous high-speed trains, weighs 815 tons at full capacity. It is more than 10 times heavier than that Boeing, and it travels on the ground. To push that mass to 340 kilometers per hour and hold it there requires a completely different category of power. The N700 delivers a combined output of 10,500 kilowatts across its entire formation. That is over 14,000 horsepower. Distributed across 16 coaches, every single one of which has its own traction motors. The train does not just pull from the front, it drives itself from end to end. The largest container ships in the world, ultra-large container vessels, run on engines producing over 80,000 kilowatts. That dwarfs any locomotive. But a ship floats. It glides through water with almost no friction between its hull and the sea. A train must overcome rolling resistance on steel rails, fight inertia, and climb gradients under full load. In that context, the efficiency of rail is extraordinary. Freight trains consume 3 to 6 times less energy per ton-kilometer than road transport. They punch far above their weight in every sense of the phrase. So what is the real secret behind a train's ability to move such enormous mass? It comes down to 3 things working together. First, steel on steel. A steel wheel rolling on a steel rail has a rolling resistance that is 10 to 20 times lower than a rubber tire on asphalt. Once a train is moving, it stays moving with far less energy. The force that would be wasted fighting friction on a road is instead converted into speed and momentum. Second, traction spread across multiple axles. A locomotive may have 4, 6, or even 8 driven axles. Each one is a separate point of contact with the rail. More contact points mean more available grip, which means more tractive force before the wheels begin to slip. Modern electric locomotives can develop starting tractive forces of 300 to 400 kilonewtons. The force required to hold dozens of tons from sliding down a steep incline applied continuously at the wheel-rail interface. Third, the torque curve of an electric motor. This is perhaps the most important point of all. A combustion engine develops its maximum torque only at a specific rev range. You need to build revs, select the right gear, manage the power band. An electric motor delivers its maximum torque from 0 revolutions per minute, from a standing start, instantly. That is why electric locomotives can pull 1,000 tons from rest without a gearbox, without a clutch, without warming up. The driver opens the throttle and the load simply begins to move. The Shanghai Maglev line in China lifts its carriages above the guideway using powerful electromagnets. No wheels, no contact, no friction. Its commercial top speed is 431 kilometers per hour. Hyperloop concepts push that logic further. Vehicles in near-vacuum tubes targeting speeds above 1,000 kilometers per hour. The energy source in both cases is electricity, increasingly generated from renewables. The train that started with a coal fire and 15 horsepower has arrived at magnetic levitation and 14,000, and it is still accelerating. The power of trains is not a coincidence. It is the product of 2 centuries of applied physics, of engineering choices that happen to align perfectly with the laws of motion. Low friction, high mass, instant electric torque, and of a relentless drive to move more, faster with less. Next time you stand on a platform and the ground starts to tremble, you will know what is coming. Not just a train. The culmination of everything humanity has learned about force, energy, and the stubborn refusal to stand still. Thanks for listening.